So, starting brand new stuff today, equilibrium, as I mentioned yesterday, is going to be a focus for 3 consecutive units. So, understanding the basics of it today is essential. So, focus your brains as we begin. People at home, have your slides out. Can y'all see that? So, what does equilibrium refer to? Well, first off, it's the return of the double arrows. If you remember, we had, whenever we were doing dissociation equations and doing things like breaking apart weak acids, they would dissociate at equilibrium. So, now that that word is a focus, everything that you'll be drawing in this unit will be the double equilibrium arrows. So, by definition, equilibrium refers to a reversible reaction where the forward rate equals the reverse rate. Notice it doesn't say the reactants equal the products. That's a big equilibrium misconception. Bless you, Dylan. Anyway, it's only looking at the fact that the reaction is happening equally both directions, despite what the concentrations of the reactants and products might be. So be careful of any misconceptions you might have. What we're ultimately going to be doing is calculating K. K is going to be our equilibrium constant. And once you know what K is, you can conclude some things about the reaction. So it's nice to be able to find your K. So a little bit about the K that we're going to be setting up. If you take a look, you'll see a reaction there. A plus B yields C plus D. And then it's put into an equilibrium equation. So what I want you to notice is that in the equilibrium equation, the concentration of the products are put over the concentration of the reactants. Keep in mind that brackets always refer to molarity there. But not only that, look at how the products and the reactants, which are on the products top, reactants bottom, are raised to the power of their mole ratios. So if you look at the equation up there, the lowercase a, b, c, and d's would be the mole ratio of the balanced equation. But you'll see that in the equilibrium equation, it's going to be raised to that power. All right. So in other words, coefficients become exponents is a way to look at it. Now, some important things though, since only concentrations can go into this equation, only substances that are aqueous and gaseous can go into the equation. You can't have a concentration of a solid or a liquid because concentrations are going to require there to be dissolved particles. Therefore, if you run into a liquid or a solid while you're doing equilibrium stuff, they'll be ignored. And you'll see that a couple times today because equilibrium equations can only take aqueous and gaseous into account. Yes?
What if there's one that's like not specified?
That should not ever happen. The only reason you run into that sometimes on assignments is, like when I'm writing your Schoology assignments, it takes a long time to write them and subscript them and go back and do it. So if they're not necessary for the problem, I don't always put them there. But in real good chemistry, everything is defined by its state. Now, one of the annoying things that AP does is they use K and KC interchangeably. Really, K for equilibrium should be good enough. But KC is the exact same thing. So, they're referring to, K and KC refer to the exact same item, the equilibrium constant. Now, KP, though, is different because KP is going to refer to a system based off pressure. Now, when that happens, the substances that are allowed to be put into the equation become even more specific because you're not going to have a pressure of an aqueous system. You're only going to have a pressure of gases. So, to summarize, if you're finding K or KC, those are the same thing. You've got to be looking at aqueous and gaseous. If you're finding KP, looking at pressure, It's got to be gases only. Whenever you start studying a reaction to look at its equilibrium, one of the things it's always going to mention is a specific temperature, or it'll just say at a particular temperature, all right, instead of giving you the value. If you find K, if you find that equilibrium constant that you're looking for, and then you change the temperature of the equation, K has now changed. So you need to know for sure then that the equilibrium constant is temperature dependent. Changing the temperature changes K. That sounds like a super good choose all of the following that are true statement on a test to me.
Say it again.
Choose all of them. I'm just kidding. That the equilibrium constant is temperature dependent. Changing the temperature changes K. So what do we use K for? A variety of things, but most notable for our intro today is simply looking at the magnitude of K. If K is above 1, the reaction is favored towards the products. All right, they're at equilibrium, but you're going to find the products in higher concentrations. If K is less than 1, then it's favored in reverse. All right, both directions happen, right? That's the whole point of the equilibrium arrow. But if you calculate K to be less than 1, it's favored in the reactants position in reverse, and that's where the higher concentrations are. What do you think it means if K is equal to 1?
They're both equally
Okay, now that Dylan said two things. Quiet, please. His first thing he said was right. He said it means they're the same. He wasn't specific enough for me to get excited. But then he followed it up with the biggest AP distractor on what K means. He said it means they're at equilibrium. If there's a K value, no matter what it is, they're at equilibrium. It would only have a K if it had equilibrium. Don't let your brain connect K equals 1 means it's finally at equilibrium. No. It's always at equilibrium if it's got a K. K equaling 1 only means that the concentration of the reactants equals the concentration of the products. So it's not favored one direction. If K equals 1, the concentration of the reactants equal the concentration of the products, and it's not favored in either direction.
But you can still say it favors both directions.
Yes, it can be negative. I'm sorry? Slide change. So, one of the things that you might be asked to do, all right, we haven't used the equation yet, we will soon, is to analyze equilibrium graphs. And you can do a whole lot from looking at one of these graphs. Now, real quick, because the bottom axis is not, dang it, is not labeled, it's time. So if you have your slides printed out, that bottom axis is time. And then the other axis is looking at the change in concentration. So here's what I know about a reaction. If the reactants are yielding products, then the amount of reactants are going down while the amount of the products are going up. That makes rational sense, right? If that's true, based on the simple direction that those lines are moving, I can identify reactants versus products. So listen again, in any reaction, if A is yielding B, that means A is going down and B is going up. If that's true, what are your reactants here? Which letters would be the reactants?
B and C. B and C, because A goes up if it's a product. B goes down.
A only is the answer.
A down.
Because A is the only line that's decreasing. A is going down. What are B and C doing? They are both going up, which means they are both products. Yes?
Does that mean A is like the reactants? It's showing the reactants?
Exactly. A is the reactant, and B and C are the products. Oh, I went to a bad color for my video. All right. So that's one of the things we can tell. Hey, there's more that we can tell. I can figure out at what point in time equilibrium was established. At what point in time did the motion become equal on both sides? And the way you see that on the graph is whenever the slope disappears for everything. The point in time where none of the substances have a slope any longer is the moment that equilibrium was reached. Now, we could debate exactly when it happens. Therefore, on Schoology and on the AP, they've got to make the answers different enough that there's no discussion about it. So while we'll debate right here, I'm sure, someone yell out a number. At what point in time does it look like all of the lines plateau?
1,000. 800. No, 750.
Now, when I look at it close, I think that it's somewhere from 800 to 900. But again, I'm not going to make this tricky. If you know what you're doing, you'll know the answer.
So what is that? 850.
That is the moment at which equilibrium is reached in the reaction. The moment at which this is now true, which is the way we should have originally drawn it anyway, since we were looking at an equilibrium graph.
So if it's time, is it like seconds?
Yes, seconds. I mean, it could be minutes, but
So that's a long time.
yeah, it's seconds. Oh my gosh, there's more stuff we can figure out.
Oh, nice.
If we compare the kinetics of those substances, I can find a mole ratio. If I look at how much they're changing and how quickly they're changing, I can figure out the mole ratio of these substances. Here's how you do it. Pick a block of time. Remember, time's going along the bottom. Pick one block of time, and I'm going to check out how much each of them change. So let's pick the first block. So right now, I'm looking at the block from 0 to 250 seconds. You with me? I want to first see how many blocks does A change in that time. If you were to round it, it never hits perfect, but does anything ever happen perfectly in here? How many squares does A cover in the first block? It covers 2, all right? How many squares does B cover? It covers 1. How many squares does C cover in the first block of time? 1. And since this is in its most reduced form, guess what I have now found?
Wait, say that again.
I've got a mole ratio. The mole ratio of this reaction is 2 to 1 to 1. And now I've added coefficients in, and I feel good about myself.
Can you pick a stupid block like 250 seconds? Like,
The-
how would you be able to tell if it was that? Because it's like super hard to.
Which is why you want to pick the one that has the most obvious. Yeah. The question was, can you pick another rate? Well, you don't want to pick one where they're already at equilibrium, because that's not going to help you. All right. So it's easier to pick one where they're as far away from it as the graph is analyzing.
Wait, Mr. C, what's the y-axis?
Time. Oh no, I'm sorry. It's the molarity, the concentrations. You can change slide and let y'all get brilliant. Here we go. Can you solve it? I want you to answer all 4 of those questions. Take a moment. I want you to identify all 3 things. What are the reactants? What are the products?
Should we do that, or do we just put straight numbers?
No, you can just put one number. That's fine.
counting, he's like still in the thingy that's just a little bit.
I mean, really, and I'm trying to show you another example that they could do, but it looks like there's an equality between the amount that they're both going up. I'll show you what I mean when I analyze it. For those of y'all that are counting numbers, you can do that, but I'm a square counter. I think it's easier.
No, I am counting a square.
I know. I see what you're saying. But watch the way I see it. Maybe you'll see it the same way. Hey, yes. What?
Why is this called rice?
That's not. It's not called rice. Rice is Monday. Rice is Monday with egg rolls. Okay. Let's get some help. Let's go talk to cluster 5, seat 2. Who sits there? Okay. Barajas, what are the reactants and products?
A is reactant, B and C are.
Okay, cool. That's on up versus down, right? Everybody agree? Okay. Let's head on over then to cluster 6, seat 6. Aspen, what did you get for the equilibrium time?
2,000 to 2,400.
2,000 to 2,400? Y'all agree?
Yes, but like I don't think it's.
Yeah, I mean, it looks like it happened earlier than that. It looks like they're trying to keep the line straight. When I analyzed it, I mean, I thought it was closer to even 600 even.
I put 400.
So, I mean, I thought it was closer to 600, but you can see how that can be a bit confusing. But again, I have made sure that it's not on my answers. But I said that, but I mean, it is at equilibrium at the point that he named. I thought it was at equilibrium slightly earlier. And now the question, yes.
No, it's not a question.
Let's go to cluster 5, seat 1. Did anybody sit? Oh, that's Isaac. Do you want to give me your mole? Don't you be upset. Do you have a mole ratio?
955.
All right, so she went 955.
I did 8.
You know what I see though? I see 9 and 4.5
Oh.
and 4.5.
So how do you-
Now, for those of y'all that are like, oh, you can't have decimals as coefficients, y'all, this is a ratio because this is the same thing as 2 to 1 to 1.
So is it wrong?
I don't believe it.
Wait, back. Wait.
If you divide all of these by 4.5, you get the correct answer. And I bet if you look close, y'all can now justify my 4.5s, can't you?
I mean, it's barely 0.5.
Wait, so how did you get 2 on 1?
Because on the other one, A moved 2 whole squares, B and C moved 1 square, and it was already a simplified ratio. Alyssa, the equilibrium time is the moment that, whoa, it got big, is the moment where all 3 lines have no slope.
It's when they go straight.
This is, I don't.
Glad we all like each other. Let's move on. All right, so let's talk about actually using the equation that I introduced at the beginning of this lecture. Oh my God, look at that. Faller shows up and she's smarter than all of us. Fix it. If you wrote it down wrong, fix it, because it was wrong. Fix it.
Why are you so bad? You wrote it wrong.
Does it matter which way the arrows point?
Nah.
Like if like the top one pointing.
Nah. No. All right, so as we start using the equilibrium equation, and again, that's the one where we have the the concentration of the products divided by the concentration of the reactants, and those items will be raised to the power of their coefficients. We'll do that in a moment. I want to point out that K is unitless. I always get very excited when we have a value that is accepted as unitless, because it's less to think about. So your equilibrium constant will never have a unit. Now, here's an important thought, though. AP will give you a point for writing an unsubstituted equation. What I mean by that is when you look at this problem that's about to show, that's showing up right now, will you change the slides? When you look at this problem, if instead of putting the numbers into your equation right away, if you just set up K equals and put the substances that are products over the substances that are reactants and show what the equation looks like without the numbers, but with the parts of the equation, you get a whole point for that. We want to be in the habit of showing every unsubstituted equation that we can. All right, and I'm about to do it, so you'll see right now. Let's look at the equation, at the question. The following reaction is at equilibrium, all right, at a particular temperature, because it has to be at only one temperature or it would keep changing everything. And then it gives you the molarities of everything there is. So here's what I'm going to do first. I'm going to say, all right, well, K equals. I'm going to find my product, which is HI, and I'm going to raise him to the power of 2. Do you see why? Because it's just the constant of K, but it could be there or not be there. They're the same thing. Because we always raise to the power of the coefficients. Hey, are we supposed to put the product into this? Is this product okay to go into this equation? Because it's gaseous, right? Because remember, if it was solid or liquid, it's ignored. But we're good. They're all gases, right? So we can just go for all of them. Over the reactants, my first reactant is H2. My second reactant is I2. Again, everything's a gas. This is known as an unsubstituted equation. I just showed you what it looks like with this equation without putting numbers in it. Always do that. But now let's put numbers in it.
Sorry.
Yes, ma'am.
It cuts off at the beginning. What is it supposed to say? It says D the.
I don't know.
It looks like because it does that a lot when you're sliding.
Yeah, I mean, it's not whatever it is, it's unimportant. Well, that wouldn't really make sense there. But all right, so let's substitute in. My concentration of HI is 0.3. My concentration of H2 is 0.012. And my concentration of I2 is 0.15. Yes. Yes. Now, guys, careful with your exponent there. Last period, we were getting weird. I mean, 75% of the class all got the right answer, and the other 75% of the other 25, I can do math. The other 25% of the class, all right, put the same thing into their calculator, and they all got the same wrong answer. So, careful. All right, it's a bummer to make it this far and then miss it because you don't know how the buttons work. Get an answer. We're going to call on somebody. Let's go talk to somebody.
What?
They yelled it. Cluster 4. Seat 6, Aspen. Sorry. Aspen, what'd you get?
50.
She said 50 in a high-pitched voice. All right. She said 50. Is there anything you want to add to the number? No, you're right. That's the right number.
Oh, okay.
Is there anything you want to add to the number the way I have it written, though? A decimal. Yeah, you need a decimal.
You can just get this.
What are the units of your answer?
None.
There are none. Yay! Now, if you got anything but 50, your order of operations are doing something weird in your calculator. All right, in which case you need to go slower. Like really break it down. Square 0.3 and get a number. Multiply those and get a number. Then slowly divide them because you're putting it in wrong.
I got 0.1. I know it's something else.
Now, if you're able to do the chemistry but not the calculator, at some point, guys, we just have to sit down together. I can't do it during lecture, but we have to sit down together and show how parentheses, extra parentheses, can protect you from getting it wrong. Is this reaction favored in forward or reverse or neither?
Forward.
Favored forward, because if the magnitude of K is greater than 1, even though it's at equilibrium, it's favored forward. We're going to do another one of these problems at the end of the lecture, but I need to show you the harder equation in case we need to spend extra time on that. So let's look at another thing that might happen. I've got some really good news, though. That politically correct equation, and the reason I call it that is because that's the way I was going to help you memorize it. Do you see politically correct written in it? Do you see politically correct? It was the mnemonic I was going to use to make you memorize it. Anyways, it's now on the sheet. It's now on your AP sheet. So if you wrote down, memorized it, or printed the slides, get rid of it. You do not have to memorize that equation. It is printed verbatim on your AP reference sheet. So yeah. What this equation is it gives you the ability to convert between Kp and Kc. Remember, Kp is looking at the same thing based off pressure. Now, for these, though, only gases count when you're looking at pressure because the other states of matter don't have a pressure. Therefore, you've got to be very careful on not letting a problem trick you into including molarities of non-gaseous items. Now, let's talk about what's in the equation, though. All right, you've got your pressure constant, you've got your non-pressure equilibrium constant. R is something that you might remember from gas laws in pre-AP. We used it in Pivnert, but anyhow, it's a constant value that you don't have to memorize either, also on the sheet, of 0.08206. T stands for temperature. It must be Kelvin. You should be at the point now where you don't have to remind yourself of that.
What's the unit of that? 206.
It's latums over mole Kelvin. But the reason it's set up like that is so everything cancels out everywhere else beautifully. But anyways, it's liters per atmosphere over moles per Kelvin, over moles Kelvin. No, it's printed on your sheet. The issue that you might have with this equation is that last thing, the change in N. If you remember from Pivnert, N stands for moles. So this wants to know what is the change in moles across the reaction. Now, as I told you in an earlier lecture, sorry, everyone's looking at my stuff. As I told you in an earlier lecture, anytime you see that delta, that triangle, it's always the final minus the initial. So what we need to simply do, listen, is take the total amount of gaseous product moles minus the total amount of reactant gaseous moles. And I'll show you what I mean in the problem in just a moment. Go ahead and show us that problem. Okay, so we know, let's just get the equation written up here, that Kp equals Kc RT to the change in N. All right? Now, this gives you a specific situation, but it's really just a plug and chug to convert between Kp and Kc. So let's take it slowly. It does give you your pressure constant here of 0.25. And it wants you to find the constant of the non-pressure equilibrium. Our R value is constant at 0.08206. Our temperature is already given in Kelvin, so that's a hooray moment, 1100. And now the fun moment. How many of the substances, oh, I'm sorry, SO3 is gaseous. This one did cut off and it hurt us. SO3 in this problem, it's cut off. It's gaseous. So add it if you don't have it. At home, the product here, SO3, is gaseous. It's supposed to be there. How many of these substances are we going to take into account for the pressure? All of them. They're all gaseous. Hooray. How many total moles? Remember what you look at for moles, it's the coefficients. How many total moles of gas are there on the product side?
2.
There's 2. Everybody see where she got 2? She looked at the coefficient. Careful on this next one. How many total moles of gas are there on the reactant side?
3.
There's 3. Because there's 2 of SO2 and 1 of O2. What is the difference between them? Negative 1. Products minus reactants. And now, it's algebra. I will solve with you on this one, since we're having a little bit of issues. So if I'm going to simplify slowly, I would go 0.25, and then you can type this into your calculator exactly the way it looks. In parentheses, I'll put 0.08206 times 1100, close parentheses, raised to the power of -1, and it will give you a simplified value. Yes? The 2 and the 3? So, what I did was I looked at my moles of gas over here on the product side. It was 2. I looked at my total moles of gas on the reactant side. It was 2 here and 1 here. So 2 minus 2 and 1 is 3. 2 minus 3 is -1. I get 0.011x. Solve.
This doesn't have units, right?
Nope. None of your equilibrium K's do. I get 23. How do we feel about our life decisions? I should have been a painter. $23. Are you talking to me? You try one. Careful. It's just plug and chug, really, once you realize that you're using this equation, which I'm giving you tunnel vision because I'm telling you that's what we're doing. But once you pick the equation, you should be good, but careful with delta N. Call me over if you get stuck.
Where did I get it from? Where's the Oh, yeah, it's Mars. Mars is going to die.
It's just normal numbers.
I mean, that was pretty good. I just didn't know how to like go out. Yeah.
They're coming.
Alright, I'm on a time crunch, I've got to go. Not leave. See y'all later. Alright, so let's plug and chug. What I see here is I've got a KP of 1.04. I see that I've got a KC that's missing. I've got an R of 0.08206. I've got a temperature given to me of 852 Kelvin. And my change in moles tricked some of you. My total gaseous products is 4. They're both gases. There's 3 of one of the other, 4 total. My total gaseous reactants, there are none. What number represents none? 0. 4 minus 0 is 4 because there's 2 products, both of them gaseous. 1, 3, 1, 1.
Wait, so is the big number that you get from that right?
The big, I mean, before you divided 1.04 by it. All right. Now, as you simplify this, you'll get, yes, a big number here. You'll divide this number by that big number. And the final answer that I get is 4.35 E negative 8.
I got the same answer.
Guys, think about this. Here, for those of y'all that are getting big numbers, this is a big number. If you divide 1 by a big number, you better get a tiny number, right?
Mr. Cummings, I think somebody keeps changing the calculator settings.
Yeah, we have goblins. They're annoying. Switch, please. Okay, moving on. The final idea that I want to put into your brain is this. They like to ask conceptual questions about the connection between the forward and reverse reactions in regard to K. realize that everything we're doing right now, even though they're at equilibrium, you're still identifying reactants versus products. Therefore, since the reaction can go both ways though, they can ask about the items in the opposite direction. In other words, the products can become the reactants. And if they were, everything would be put somewhere different. All right, because right now you're putting products on top and reactants on bottom, or you're subtracting mole products minus reactant products. So if the reaction were to go, you were to analyze it the other way, it would change stuff up. But here's the good news. If you find K for the forward reaction, and then it says, well, then what's K for the reverse reaction? It's really just flipping everything around. The mathematical word for that is reciprocal. And the AP likes you to know that word. If it asks you to find K for the backwards reaction, when you're putting the information into the equation, you could just put the information in the other spots to get it. All right? I know that, but they like to ask questions conceptually, not using numbers, and reciprocal is good there. But what I'm saying is that if this is the answer for the forward reaction, and it wants to know what is K for the reverse reaction, well, that would be 1 divided by that number, because that's the reciprocal of that number. Do you understand what I'm saying? Because right now this number as a whole number is over 1. All numbers not in a fraction are over 1. So if you find the reciprocal of any whole number, suddenly it's 1 over that number.
Will it ever change to not?
I mean, it would have to be a fraction for starters if it's not a 1. Go to the next slide, please. I'm going to work this problem with you. I just want you to work through it with me because we're too low on time for me to cut you loose. But let's look at what this wants us to do. I'm going to move kind of quick, and I apologize. But for y'all that watching the video, pause so you can keep up with what I'm doing. It wants to know K in reverse. But I'm going to solve it forward first and pretend that it gave me parameters that made me do that. All right, so here we go. It gives me 4.3. Let me rephrase. I have to have molarities, right? I have to have concentrations. It's brackets that go into my first equation. By the way, we're back to the very beginning of the lecture now. We're no longer going KP to KC. You've got to be able to see that. I mean, look, KP is mentioned nowhere. So we're obviously not doing the type of problem we just did. You've got to be able to compartmentalize. We're back to the first equation. Concentration of products over concentration of reactants. All right? But I don't have concentrations. It's giving me moles and liters. Can you find concentration, molarity, from moles and liters?
Yeah.
Yes, very easy. It's moles divided by liters. So for chlorine here, I'm going to go 4.3 over 5. Do you see where I'm getting those numbers?
Yes.
All right. For my NOCl, I'm going to go 3.1 over 5. I'm dividing all of my moles by the liters. And then for my NO, I'm going 6.5 E2. 2 or negative 2? Negative 2 over 5. And then this is going to give me my different values. And it looks like the values that I get are 0.86 molar here. I get 0.62 molar here. And then 0.013 molar here. All right, cool. So I know what to put into my equation now. What's the next thing you should do on AP at this point? Write an unsubstituted equation. You should write K equals, and then your products, NO to the power of 2 times Cl2 to the power of 1 over your NOCl to the power of 2. Write the unsubstituted equation first, but I'm going to continue due to time constraints on that bell. So what I want is I'm going to find my K. My product is my NO, which was 0.013. Raised to the power of 2 because of the coefficient times the Cl2 concentration, 0.86. All right, with no coefficient, so no power, over my reactant of NOCl, which was 0.62 molar. And again, he's raised to the power of 2 due to the coefficient. Now remember, this wants the reverse. So when you run this equation, you're not going to get the answer to the problem. You need the reciprocal of the answer to the problem because you're solving this forward right now based on where the reactants and products are. I'm going to keep going for you. I don't care about them. No, I love them all. You'll have a great weekend, but I'm just going to sit here and teach by myself. Anyways, so for K here, the solution for this, if you're careful, is going to be 3.8 E negative 4. All right? Now, if it didn't want K in reverse, that would be the answer. All right? But it wants it in reverse. So if I take the reciprocal, it then becomes 1 over 3.8 E negative 4, which again is really just dividing that as written in your calculator. So if you take that and go 1 divided by 3.8 E negative 4, you end up with 2.6 E3. And that would be your K for the reverse due to the reciprocal.